Hello everyone, welcome back to CpE2301. This is Unit 4 and then we are now in Lecture 5. So in this lecture, we'll be discussing about the state reduction and state assignment, and also a example circuit applying the sequence detector of your sequential circuits. So this is a state reduction. So in reduction of the number of flip-flops in a sequential circuit is referred to as a state reduction problem. The concern with procedures for reducing the number of states in the state table while keeping the external input and also the output requirements are unchanged. So basically in designing a circuit, we retain the input and output bits or the input and output devices. What we can reduce is the internal circuits of your combinational or sequential circuits. So a reduce in the number of states may or may not result in the reduction of the number of flip-flops. So in reducing the state, so this is the rule here. So the two states are said to be equivalent if for each member of the set of the inputs they give exactly the same output and send the circuit either to the same state or to equivalent state. So which means that if these two separate states have the same input instance while at the same time having the same output, and its next state is also the same. So to further demonstrate about this one, here's an example. So for an example, this is a given state diagram. So we have here around 7 states, namely state A, B, C, D, E, F, and G. And then it has its own directions. If the input is 1 or 0, and then it also has its own outputs. To start in state reduction, we transform the state diagram into a state table for more easier visualization. So this is now the equivalent state table. So we have here the present state, the next state, and then the outputs. And then this is the inputs, x equals to 0 or x equals to 1. So for example, if state B here has the next state of C when the input of x is 0, or the next state is D when the input x is equals to 1 for its next state. So to reduce this one is based on the definition is to find a state, for this case a present state, that has a next state equivalent, almost the same scenario. At the same time, the output is also the same. So for in this case, let's say this one, state E in the present state and state G in the present state has the same next state A and F, and also the same output 0, 1 and 0, 1. So in this case, that state E is the same in state G. So we can equate those states. So remember that if we equate E and G, we must also change that the value of G or E becomes the same. to the ones that will be removed. So for example, if we removed state G here, so this G becomes an E state because E and G are just the same. So is there anything else that we can reduce from this state table? So since this becomes an E, you can also see that this line here or row is also the same with this row. So we can reduce this one. So if we remove F here, the F being used here is now equivalent to D. So once removing this one, okay, so we have now 5 states. So basically this is now your reduced state table. So if you ask that this state here has the same next state, we cannot reduce these two because the output is not the same. The output of your state C here is 0 and 0 for x equals to 0 and x equals to 1, and for state E that is 0, 1. So both states are not the same to each other. So basically this is now the reduced state table. And then you can now redraw the state diagram to its equivalent reduced state diagram. So previously you have 7 A, B, C, D, E, F, and G states. So you have now in the reduced 5 states. So in state assignment, these are state variables assigned to your to ordered binary numbers or codes. So when designing the circuits with flip-flops, it makes the binary bits unique to the other states. So initially, we assign the states with a variables. So previously here, in the previous example, we have named the states by letters A, B, C, D, and E. By using the state assignment, we can transform or assign these states into equivalent binary values. So I highlighted here that it should be in the ordered binary numbers or codes. So it is not just limited to binary numbers, but into a binary codes such as gray code, unique ones, or unique zeros. You can use this equation above as to identify the number of binary bits to be used using this n, where m is also your number of possible states to be used in the state diagram. So for example, if we take the example earlier, so we have there 5 states, A, B, C, D, and E. So we can have here 3 possible state scenarios. So using binary, gray code, or one hot, or one cold if it is unique zeros. So just to give this one step by step, we'll just use the previous example, the reduced state table. You want to transform this one into, or assign the states into its equivalent binary bits using binary assignment 1 here. So to use the equation, so m here again is the number of states. So how many states there are? So there are 5. And then to solve this one, we use logarithmic, because the left side equation here is an exponent, and we want to get the value for n. So by multiplying log here, so n times log 2 here, and equals to log 5, and then log 5 divided by log 2, that will becomes 2.32. So that is now the value of our n. But since there are no fractional states, so there's only 1 or 0 states, or in a whole number. So that's why we round up this number to 3. So therefore there are 3 bits to be used for your states. So it starts with 0, 0, 0, 0 and 1, 1, 1. So first here, since state A is our initial state, so we can use that one as a 0, 0, 0 state, and E becomes 1, 1, 1. But we want to have it in order, so this is A 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then this is 1, 0, 0. So the remaining unused bits are for other states, if this is around 8 states. So we'll just substitute that one here. So in result, this is now the substituted or assigned states. So later on, when we convert this one into flip-flops, it would now be easier. So in this case, there are 3 flip-flops. So let's now proceed with the sequence detector circuits. So for this part of the lecture, it would be best to demonstrate this one in a simple problem. So for this problem, I'm giving you an example here where to design a circuit that it recognizes the occurrence of a particular sequence of bits. So regardless of where it occurs in a longer sequence, it has to have one input W, output Z, and a direct resets on its flip-flops to initialize the state of your circuit to all zeros. The circuit is to recognize the occurrence of the bits of 1101. So this is the sequence we want to find. So we input this sequence in W input, and then it makes the Z output equals to 1 when the previous inputs of your circuit were 110 and then the current input is a 1. So it will only becomes 1 if the value is 1101. Again, we have only one input or 1 bit input, so how can we store these 3 binary bits 110? So remember that flip-flops is a storage element based on the previous lecture, and then otherwise the output is 0. So there's only one scenario that the Z becomes 1. So that's the time when the previous sequence is 110, and again the current input is 1. So just to clarify again, so there we have here 3 IOs, 2 inputs, W and resets, and output Z. So that's only one output. So to start this one, we need to generate a state diagram based on the scenarios given by the problem. So I'll just give you an example input sequence here, and then the sequence bits to find here again is 110. So how many 110 occurred in this sequence? So I'll be highlighting there all of the sequences of your 1101. So we have here the first occurrence, the second occurrence here, third, and fourth. So there are 4 occurrences of this sequence in this input sequence. And then if you ask why this is included, this one here, this is included because that is still the same scenario, even though it is from the previous sequence. Since the sequence is still ongoing, so this is still recorded as 1101. So let's start doing the state diagram. Okay, so even though I have already given this one, so I'll be explaining this one by one. So we don't know yet at first how many state diagram states there are in the state diagram. So we start at state A, your initial state. So from your initial state, you have received a 1 input from W. So for this state diagram, I won't be including reset since based on the problem, it is a direct resets on your flip-flops. So what it means is that we are using the asynchronous resets of your flip-flops. So we retain or we only use the W inputs. So when the W is 1, so from state A to state B, so you have now 1. And then from state B to state C is another 1 from the next input. And then state C to D if the input is 0. And then state D to E if the input is 1. So we have now the sequence 1101. So after that, we can now complete the other scenarios of your state diagrams. So from state A, since this is 1, so the other input is 0. So where does it goes? So it goes back here. Since the sequence it did not start, so it goes back to its original state or the initial state here. And then we have node B. So from the state B, we have already have 1 stored to our previous flip-flop here. So when it goes to 0, so 1 0 is no longer a sequence from your original sequence to find. So that's why we go back to state A. In state C, your alternate sequence here is 1. So I place the arrow here goes back to C because on this state you have already 1 from this one, 1 from this one, and then you go back or use another 1 here. So it is a 1 1 1. So even though it is incorrect, sequence 111, but it still finds another sequence that when C becomes 0, it becomes 110. So this is 2 in this sequence here above. So this is 1, 1, 1. So 1, 1, 1, and then 0. So you have now 0. So it has a chance to get the same sequence 1 here if the next sequence is 1. So this is being considered here. So for state D here, so when it becomes 0, if the input is 0, so it goes back to state A. So that's because that the input is now 1, 1, 0, 0. So this is equivalent to this scenario here. So in this case, that is no longer the same as your sequence bits. That's why I move back that one here at state A. And then lastly here is that state E here goes back to C, because in this case this is already 1101. So we can treat here the 1 here is the initial 1. So it becomes another 1 here. So 1, 1, 0, 1. So that's why the sequence around around here. So this is 1101, and then you can use this one to get another sequence 1101. So that's 1, 1, 0, 1. And then if you ask why you have this arrow here, so in this case is that when it becomes 1101, if the input of your state E is 0, we go back to state A. So if you want also to draw the state diagram for the reset, so for in this case I just separated this one so that we can identify that in state A, but either the reset is 0 or 1, it goes back to its self, state A, because this is your initial state. That's why it doesn't matter whether the reset is 0 or 1. But on the other states, if the reset is 1, if it is an active high reset, we go back to state A, and then the output is 0. And then also if you observe everything here, the output is everything is 0 except for this part, because this is the only one signifies that it completes the sequence 1101. So after this one, we translate this one into a state diagram, from state diagram to state table. So here, so this is now the equivalent state table. Okay. And then we try to reduce this one if there are anything that we can reduce. So for in this case, we can further reduce this one on these two rows. Since A and C, and then 0 and 0, 0 and 0. So therefore state B and state E are the same and can be reduced. So if we remove state E here, and then equate the E here, becomes a state B. So this is now the reduced sequence detector state table, and then the equivalent state diagram here below. So from 5 states, we have now 4 states. And then let's say we use the flip-flops in creating the circuit. So how many flip-flops we're going to use? So we use the equation, and then we get 2 flip-flops. And then since we have 2 flip-flops, we have 2 bits in our state assignment. So A here is 0 0, B is 0 1, C is 1 0, and D is 1 1. So on the left side is the summary from the previous, and then the right side here is the equivalent using the state assignments. And then if you want to more preferred state table equivalent of this one, so we can use the the state tables. So this is the equivalent state table, expanded and then used to separate the QA and QB for 2 flip-flops. So what we want here is to find the flip-flop inputs. So what we already have is your present state and next state outputs here for your D flip-flop. The inputs is the missing piece. So since we are using D flip-flops for our circuit, so based on the equation or the state equation for your D flip-flop is that D is just equivalent to your Q N, or the next Q, or the next state Q. So in this case, we just copy the values in the Q next to your D values. Okay, so after this one, after getting your flip-flop inputs, we can now design your circuits. So in designing your circuit, so we need to identify your circuits or the combinational circuits of your D flip-flop inputs. So this is for the DA, DB, and then the Z outputs. And then after getting this one, we can now construct your circuit. Okay, so this is now the final circuit for the sequence detector for this problem. But the missing part here is that the direct resets of the flip-flops. So again, the direct resets are your asynchronous resets found in your D flip-flop. So we'll just use that one. So for this case, circuit now below here has now the asynchronous resets. So we have here 3 inputs, including the clock, and then 1 output here. So that's now the circuit. So that ends my lecture. Thank you for listening. And then if you have more questions, kindly contact us.